Physics feels abstract. It explains planets, particles, and distant things, but it also explains something much closer. It explains you, not in a clean textbook way, in strange ways. Ways you hear, ways you feel, ways you usually ignore. And sometimes, particles cross barriers they're not supposed to. Inside your body, physics isn't theoretical. It's happening. Strange physics inside you. Did you know quantum physics isn't just for labs and lasers? It's happening inside your body right now. Quantum tunneling in body. So to explain quantum tunneling in the body, we've got to start with how weird particles actually are. When you zoom in far enough, way beyond atoms, you stop dealing with solid little marbles and start dealing with probability waves. Every particle, whether it's an electron, proton, or neutron, acts partly like a wave, a fuzzy cloud of possibilities that says the particle is probably around here. Now, according to everyday physics, if there's an energy barrier in the way, like a wall that's too high, a particle with less energy shouldn't be able to cross it. It'd bounce off and return. But quantum physics doesn't play by those rules. A particle's wave doesn't just end at the wall. It bleeds through it. There's always a tiny probability that the particle's wave extends to the other side. And sometimes, that probability becomes reality. The particle doesn't climb over or break through. It just appears on the far side, as if the barrier didn't exist. That's quantum tunneling, when the impossible becomes statistically inevitable, given enough time. The wall has stood for 1,000 years.
But it has not seen the power of Valyrian dragon fire.
That's not a thing!
It is now. Dracoris!
That's it? A bird hole? This is not how physics works.
Neither did your resurrection, John.
Still work better than Season 8.
Inside your DNA, the rungs of the ladder are held together by tiny hydrogen bonds, like molecular handshakes between nitrogen and oxygen atoms. Normally, each hydrogen sits closer to one side, forming something like this, where it's bonded to nitrogen and just loosely tugged toward oxygen. But hydrogen atoms are ridiculously small, just one proton and one electron, so quantum effects hit them hard. Every now and then, instead of staying put, one of these hydrogens tunnels straight through the energy barrier separating the two atoms. In an instant, it switches sides, turning strong bonds to weak bonds and vice versa. That single microscopic hop, a hydrogen quietly teleporting between atoms, can shift how the DNA base pairs bond, and this is a mutation. That might sound bad, but it's actually what allows evolution to happen at all. Tiny random mutations are how new traits and adaptations appear over generations. Tunneling also keeps your metabolism alive and fast. In chemical reactions, atoms or protons often need to move from one molecule to another. Normally, they'd need a certain amount of energy to overcome the activation barrier, the hill they must climb to react. But quantum tunneling gives them a shortcut. Instead of waiting for enough thermal energy to roll over the hill, the particle simply tunnels through it. This is a huge deal for enzymes, the biological catalysts. When scientists study enzyme reactions closely, they find that protons and electrons often tunnel during key steps, letting reactions happen millions of times faster than expected. So what's tunneling in your body doing for you? Everything. It's part of your metabolism, your DNA maintenance, your cellular energy production, even the chemistry behind your thoughts, all exist because the universe occasionally allows the improbable. Static shocks. When you walk across a carpet, your shoes rub against millions of tiny fibers. The rubbing transfers electrons, literal subatomic currency, from one material to the other. Depending on the materials, you either lose electrons and become positively charged, or gain them and become negatively charged. This is the triboelectric effect. Now your body is carrying an excess electric charge, and because you're a decent conductor, that charge spreads all over your surface. The problem? The air around you isn't that conductive, especially when it's dry. So the charge has nowhere to go, it just builds up, waiting for a chance to escape. And that's why as soon as you touch that doorknob, you get shocked. Metal is a conductor, which means electrons can move through it easily. The air gap between your finger and the metal is normally an insulator, but as the electric field builds, it pushes past the breakdown voltage of air, around 30,000 volts per centimeter. Suddenly that air isn't insulating anymore. The molecules ionize, creating a microscopic lightning channel. Electrons leap across the gap, equalizing the charge difference in a fraction of a second. You feel it as a sting, see a spark. Boulder, they say this land's cursed. Anyone who walks it gets struck by the earth itself. You feel that smelly, paranormal activity? It's the hay boulder. It's dry. It's static. We're literally shocking ourselves. So, no curse. No curse. Don't let the word 30,000 volts freak you out, though. The energy involved is tiny. It's fast, flashy, but harmless. The reason it feels painful is that the discharge happens so quickly that your skin nerves react as if you've been stabbed by an electric mosquito. So what's actually happening to your body when you charge up? You're basically a giant capacitor. A capacitor stores charge by separating positive and negative charges across a surface. When you shuffle around in socks, electrons move off or onto you until your potential difference relative to the environment is several thousand volts. You can literally measure it with a voltmeter. Some people can hit 10,000 volts just walking across synthetic carpet in low humidity. That's why static shocks happen more in winter. Cold air holds less moisture, which means it's a worse conductor. Dry air turns the environment into a Faraday desert, perfect for charge buildup. If humidity were higher, tiny water molecules floating around would act as bridges, letting charges leak away quietly instead of waiting for a dramatic exit. And if you've ever noticed electronic equipment acting weird when you zap it, that's because static discharges can fry sensitive circuits. Those little sparks can carry thousands of volts, and while it won't hurt you, it can absolutely vaporize transistor gates thinner than a bacterium. That's why engineers use ESD protection, static wristbands, grounded mats, and conductive shoes to keep from turning microchips into smoke grenades. Ever heard someone cracking their knuckles one by one and thought they were breaking their own fingers? Turns out that sound isn't bone snapping, it's physics at work inside their joints. Joint cracking. Inside every movable joint, knees, knuckles, shoulders, you've got this sealed little space called a synovial capsule filled with a thick, slippery fluid called synovial fluid. It keeps friction low, cushions impact, and prevents the bones from grinding each other into chalk dust. It's made mostly of water, with a cocktail of proteins, sugars, and dissolved gases like carbon dioxide and nitrogen floating around in there. When you stretch or twist your knee suddenly, the bones pull slightly apart. The capsule's volume increases, but the fluid doesn't have enough time to even out the pressure, so the pressure drops fast. And when pressure drops, gases that were happily dissolved in the fluid suddenly can't stay dissolved anymore. They come out of solution in the form of a bubble. That bubble forms explosively, and the sound of it forming, that tiny rapid expansion, is what we hear as the pop. We've done it! The lost tomb of Pharaoh! Let's open it! Don't! It's cursed. It's starting, I told you. I am out of here. Relax, that's just my knee.
He ran thinking it's a curse.
Exactly. Wait, who said that? Huh?
Was that my knee?
Scientists call this tribonucleation. It's not bones colliding or tendons snapping, it's fluid mechanics right in your knee. Back in the day, people thought the sound came from the bubble collapsing. You know, like when bubbles pop after you blow bubbles. But high-speed MRI scans in 2015 settled the debate. You can actually see the bubble appear the exact moment the sound happens, not when it disappears. That means your knee pop is literally the sound of a bubble being born, not dying. Which honestly is kind of poetic. A brief flash of existence followed by nothing. That bubble hangs around for a bit, by the way. About 15 to 30 minutes before it fully dissolves back into the fluid. That's why you can't crack the same joint again immediately. The gas has to slowly dissolve under pressure before you can make another one. Okay, so if it's just bubbles, why do only some joints crack and only sometimes? That's a mix of anatomy and timing. The knee is huge. Large capsule, high fluid pressure, strong leverage from your leg muscles. That means the mechanical force can cause a steep enough pressure drop to trigger cavitation. Your wrist or toe, not so much. Smaller spaces, smaller forces. Sometimes the angle or speed isn't enough to cause the bubble to form, which is why your joints seem unpredictable about when they pop. And no, cracking your joints doesn't cause arthritis. Decades of research say the damage theory is a myth. One physician, Donald Unger, famously cracked the knuckles on only one hand every day for 60 years. The hand was fine. The only lasting effect was winning an IG Nobel Prize for Science done purely out of spite. Hydraulic pressure in body. When you stand up suddenly, you feel dizzy. That's your hydraulics failing for about 2 seconds. When you're lying down, your blood pressure is evenly distributed. But the second you stand up, nearly a fifth of your total supply rushes toward your legs under gravity. That means for a split second, your brain's pressure and oxygen levels drop sharply. And insane thing is, your body catches this failure instantly. Within 1 to 2 seconds, baroreceptors' built-in hydraulic regulator of body, they signal your nervous system to crank up the pump. Your heart starts beating faster and stronger, and your arteries squeeze tighter to push blood back up. Within seconds, pressure stabilizes. Crisis averted.
Finally awake. Time to rise. Where's the blood? Great. I wake up after 400 years, and where is the hydraulics?
Your entire circulatory system is full of these wild reflexes. When you lift something heavy, your body automatically tightens your arteries and veins to keep blood pressure up under load. When you get scared, adrenaline tightens everything even more, redirecting flow from your stomach to your muscles. When you sleep, your blood vessels relax, dropping pressure so your heart can coast in low power mode. It's an entire network of flexible pipes that can sense, adapt, and self-balance in real time. A hydraulic system smarter than anything humans have built. So next time your body does something weird, a pop from your knee, a jolt from a doorknob, or that brief blackout when you stand up too fast, remember, none of that is random. It's physics, chemistry, and a few billion years of evolution quietly doing maintenance. You're not breaking, you're recalibrating. If you enjoyed watching this video, watch this video on why your body glitches while you sleep on purpose. And that's all for today. Thanks for watching.